Hello, everybody. I've been asked to do this dozens, if not even hundreds of times. And today, finally, the time has come where we will implement our own raycasting engine in C. What is raycasting? Raycasting, you've all probably seen it from games like Wolfenstein 3D, which is actually a game that is derived from a two-dimensional map such as this one. And raycasting is a technique to derive from such a two-dimensional map a 3D world in which you can navigate. All of this is basically a geometric hack. Basically, you generate some map like this, and then from the player's perspective, you shoot out rays in all directions, just as if you were scanning the space around you. And wherever the rays hit, you calculate the distance to that point. And then based on that distance, you calculate the height of those walls. So the closer a wall is to you, the higher it is visualized inside the game. And the further it is away from you, the smaller it is. And that's how, from such a two-dimensional map, you can generate something that looks like 3D. And actually it is 3D. The downside is just that you cannot move along the Z-axis. You can only move along that two-dimensional plane. You cannot jump, you cannot go upstairs, you cannot fall down anywhere. But it's a super interesting thing to do. We're going to use as a basis for this video a tutorial here, Lotus Computer Graphics tutorial specifically written for raycasting. And we're going to use as a graphics library, the lowest level graphics library that makes sense across operating systems, and that is SDL2. Why do we use SDL2? That is because SDL3 requires some custom setup. It's annoying, and SDL2 can be installed on most operating systems just using sudo apt install or whatever. It's super simple to set up, so that's why I'm using SDL2. Now you're allowed to freak out in the comments. So what we are going to do is we're going to create a directory inside our big projects directory, which contains all the projects that we did in the past. Let's create a new directory here and call it Raycaster. Raycaster sounds so nice, and especially because I started learning C like 1.5 years ago at most, and now I'm at a stage where I can write, or I hope to be able to write a Raycaster. That would be super awesome to do. We're going to have to include SDL from SDL to SDL.h. And let's write a main method, just like this. And let's have a look at the SDL setup instructions. So what we need to start with. I mean, in the end, we want to end up with something like this down here. Let's have a look. Some three-dimensional world like this one where you can see the walls and you can even move around in the scene. And to start with that, or to start anywhere, we basically need a graphical user interface with a black background. Let's set that up. So for SDL2, let's check out SDL2 init window. There are a couple of functions that we need to call. SDL2 init window. So first we need to create a window, but I think there's even another function that we need to call before. Let's have a look which functions are available here. I think it's SDL init. Init like this. Let's have a look. SDL2 init. And there's the function, and this one initializes the SDL library. It accepts a couple of flags that we can use, and flags basically determine which subsystems we want to use. For example, whether we want to use a joystick, a game controller, events, or whatever. We just want the video subsystem. So let's check how to do that. SDL underscore init and then video up here. And then STL create window, I think. STL create window. Let's have a look at that function. And it accepts a title, X, Y, width, height, and flags. So X and Y are going to be STL window. There was some flag, right, this one, STL window pause center to center the window on the screen. Centered, and same for the Y coordinate. And then the next one was the width and the height of the screen, width, height, and flags. Flags can be 0. Flags are things like, let's have a look here at the STL window flags, just to show you guys. So whether we want a full screen window, a borderless window, a hidden window, mouse focus, things like that. Maybe in the future, maybe at the end of the project, we will need to set the window to capture the mouse. So maybe we will need the mouse focus. I don't know yet. Depends on how we implement the rotation of the player. But overall, for a start, let's leave it 0 until we explicitly need it. So this creates a window. The window function, the create window function, returns a window pointer. So let's put that here on the stack, STL window, p window, or we can just, now p window is fine. P window is this. And then we create from the window. Well, actually, wait, if the window is created here, then we should already see a window being created. So let's do STL delay for the application to not immediately quit. Let's wait for 3 seconds and then return from the main function. And this should create a window that stays on the screen for 3 seconds. Let's see. So let's go into the projects directory down here. I'm already in it. Let's go into the Raycaster directory here. And let's compile this with all warnings enabled, debugger enabled, debug flag enabled in case we need it. And then the output file is going to be called Raycaster, and the input file is going to be called, or is called raycaster.c. And then we need to add the STL compilation flags. So STL2, let's check the build flags. They should be documented online somewhere. STL, and I think it was something related to package config. Here on STL2 installation, there should be something here, right? Here, this is the simplest possible build command. You just gcc compiler, define the output file name, the source file name, and then those are the STL flags. All right, okay, so they have their own executable that returns the flags. Wait, let me just show you the build command I'm using once, and let's execute. And here is the error output. Great. Too few arguments to function STL create window. So what's going on here? Right, I forgot the title, of course. So let's go here and call it the Hirsch Daniel, or Daniel Hirsch Daniel Raycaster. And now, let's put a line break here so it's more legible, and compile this again. Maybe it would make sense. Well, I want to make sure that you can always see the commands that I'm typing. So I want to show you the whole compilation command here. Note it if you need it, but it's actually quite simple one. Let's execute it and see. Okay, now we definitely have less errors, fewer errors than before. Right, and the errors basically, width is undeclared and height is undeclared. Of course, because I haven't declared those. As always, I'm forgetting to set up stuff. So let's do define width. The width of the window I want to be 900 pixels. The height of the window I want to be 600 pixels. Let's compile and execute again. And now there's just a warning. Let me show you that one. And the warning is about an unused variable. P window, right? The P window is not used. That is of course true because we are not doing anything with it. I'm just wondering why there is no output yet. So why is no window showing up? Because I'm executing. No, I'm just compiling. Oh my God. Okay. I'm just compiling it. I'm not even opening it. So I'm wondering why the window is not opening. Of course, I need to open it explicitly. And there's a window for 3 seconds and now it closes. Right. Okay. To save some time in the future, I will concatenate using the double ampersand operator here in bash, the compilation command with the execution command. So this is the compilation command and this is the execution command right here. So we compile and execute in one go now. Usually this is fine. If there are weird errors, then the execution itself will hide the errors below the window. So it's not always perfectly practical, but it's practical enough for us here. Okay. Now, how do we continue? We have a window. I would say the next step, the next thing to do is to try to draw something onto that window. And usually in SDL, it makes sense to try to draw a rectangle on the window. We can draw a rectangle on a window surface. In SDL2, drawing always happens on top of surfaces. When you have a window like this one, the black part here is the surface of the window, and this is basically the canvas you draw on. And so we first have to get the surface. And I think there's a function get window surface, it's this one. And we can get the surface object or struct from the window like this. So let's do that. And I'm super excited for the end result today, because in SDL you always do microscopic steps here and still somehow you end up with something awesome at the end of every episode. It's so much fun. P window. Okay, so this is the surface. Now we can draw something onto that surface. We can draw a rectangle. Let's have a look at SDL2 fill rectangle. There it is. This is a function that takes as input a surface as a destination pointer and a rectangle structure and a color. So we need to do SDL fill rect. Then we fill a rectangle on the surface pointer, which is the destination. Then we give it the address of a rectangle. Remember, this is a pointer type here. And then a uint32 color. The color is just color white. I will define that in a second. First, let's define the rectangle. SDL rect. Rect is equal to an SDL. Or maybe we can just fill it right away. And let me show you what the rectangle type is here. Also takes as input just x, y, width, and height. And let's position it at the center of the screen. So width divided by 2, height divided by 2. Width and height are, let's say, 100, 100. So it's a square. And the color white is define color white 0x ff 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 ff. I think it is in an RGBA format. Why is the rectangle not filling? That's because we need to update the surface. So currently we are virtually modifying the buffers of the surface, but we need to move the surface to the graphics buffers such that everything is displayed on the screen. Because you don't want to generate every graphical change immediately. You want to accumulate changes and then flush them all to your display, to the graphics buffers once. That's how I understand it. So let's update Windows Surface and pass in the window, P window. And this one, let's have a look at it so you know what's going on. Windows Surface SDL. So as you can see here, this copies the Windows surface to the screen. The Windows surface is not the actual black part on the window. It's basically just a buffer for us to write graphics to. And it's not what you see finally on the screen. You need to copy it first. That's basically what's going on here under the hood. So, and now compiling and executing this, we have a white square which has its top left corner located right at the center of the screen. Perfect. Okay, and now that we can draw a square, we can do anything, because drawing a square is the same, or if we can draw a square, we can draw a single pixel. Let's have a look at that. And if we can draw a single pixel, let's see here, you can see a very small colored pixel. If we can draw a single pixel, we can draw any graphics we want. We just have to implement the logic properly. So this is now part of the SDL skeleton. We will need an event loop that checks whether the application is running and quits the application. So, and we need to quit the application when the user presses escape, for example, to have a gentle way to quit everything. So while the app is running, this is a Boolean variable, and this could be a global variable. It could be a variable in the main method. Let's make it a Boolean. Let's make it a global variable just for fun. Bool app running is true at first. Then while the app is running, while our Raycaster is running, we will do this. We will delay a bit in SDL. Let's delay every 50 milliseconds. So that's a frame rate of 20, if I'm not mistaken. Or maybe let's delay every 10 milliseconds. That's a bit nicer frame rate wise. This should get us a frame rate of 100 frames per second, assuming that the computation that we perform in this loop later does not block the thread too much. Okay, now we still have a single pixel here, which is hardly visible to you probably, so yeah. So what if we make this bigger, and then we, for example, just create a counter variable here, starting at 0, and then we add the counter onto the x coordinate and onto the y coordinate, just like this. Let's see what happens. So I just want to show you how everything looks if it moves. Oh, and by the way, we still don't have a nice way to close the app. Now I had to force kill it. That's not so nice. So before I start it again, let's check the SDL events. So whether the user actually presses any keys. Oops. We need to do SDL poll events, or poll event. Here, SDL poll event fills an event structure. And I think there's even an example here how to use it. Right, while the game is still running, we create an event on the stack, then we poll it. So let's create an SDL event here, event, and then while SDL poll event, we pass the event structure, the address of the event structure, such that the method inside can, and that's such that the SDL poll event method can fill it for us. And then we need to check which event has happened. For example, the user quit the application. SDL quit is an event. Let's check here. No, not that one. SDL quit event. Here it is. No, I'm not sure of that one. Let's have a look at some other events here. There are a couple of events in SDL that happen. For example, when you press a key, when you move the mouse. Joystick events if you use the joystick subsystem, which we are not using. But here we can basically just do a switch case over the event type. So event.type it should be. Let's have a look at the SDL event structure and see how it's defined. Maybe we can even use our built-in, or well, the header files on the system, on my system, so to look things up. So let's check user include SDL2, and then in here SDL.h. Let's see, is there anything related to SDL event? No, there's nothing in here. So maybe it's hidden somewhere. Oh god, there are a couple of things here. There's SDL events. Is SDL event defined here? Maybe. There's SDL event type, drop event, SDL event, right? And this is a big structure. And as you can see, it has as a, oh no, this is a union. Okay. So we can check the SDL event type here. And then we check whether the type is case. What is the type? We want an SDL quit event. Quit, SDL quit, there it is. The types of events that can be delivered. And one of the first one, the second event that is defined is the quit event. So let's check SDL quit. If it is a quit event, then we set app running to false. And this means that in the next iteration of this loop, the app will exit. Let's just break the loop and let's see what happens. Can we now do anything? Now we see the rectangle or the square expanding, which is great because this is what the counter here is doing, because we're incrementing it here using this postfix increment. And at the same time, we can quit this application using the quit button in the top right corner. Perfect. And now comes the actual raycasting type. Now we have an application in which we can draw things. We see that things are refreshing and that they are moving. And now we can check out what raycasting stuff we can do here. So let me just clean up my browser and have a look. What is the core principle of raycasting? Well, first of all, the basic idea of raycasting is that you have a two-dimensional map in which you define blocks of walls, right? And here in this case, the player is defined as this green guy, and the player looks around on the map. He has a field of view. And within that field of view, the user can look around. Basically, the user scans the area around himself and checks where the ray extending from his eyes is crossing the walls, basically. Right, so for example, in this case, this ray extends from the user here, and then at some point crosses the wall, is inside the wall, and then we can count the distance between the player and the wall, and based on the distance, we can draw the height of the wall on the screen. So I would say the first basic building block that we can code here right now without so much logic would be either drawing the map now. Well, not drawing the map in 3D, obviously, or we could define the map, or alternatively we could draw some vertical lines. I would say we should define a map because that is where it gets exciting. So in case of this tutorial, the map is basically a two-dimensional array. This is fine. Let me just check. Oh no, let's not cheat. I will define it myself. So basically, what we want is we want to have an integer array. And I always forget how arrays of arrays are initialized. Array of array in C. Two-dimensional arrays. Okay, basically it's a nested structure of arrays. Right, we have a matrix. Okay. And this notation is matrix 2, 3. This means this one has 2 rows and 3 columns, or 2 columns and 3 rows, depending on how you interpret it. Yeah, depending on how you interpret it. So let's call this the map array. And the map has a fixed size. The map has a fixed size. Let's just set it to... Oh, this is not so simple. How should we initialize the map? Let's make it 10 by 10. 10 by 10. It's a map 10 by 10. Or even simpler. Let's make it 5 by 5. I mean, later we can maybe make it bigger. I don't know. Let's just start as simple as possible. And we start somehow using some contents here. For example, 0 means no wall. Then let's just say we don't have any walls here. Does that make sense? Or maybe let's put a wall here. And then no wall here. We have to make sure we have to be careful that we always put only 5 places here. And then maybe let's put a wall here, no wall here. I have never designed a map for a game, so please bear that in mind. I'm not the best designer. And then maybe let's do this. And always keep everything uniform, such that it looks nice. And just 2 more rows. Let's put a wall here. Put no wall here. This is the empty space in the middle. This is empty space. This is empty space. This can be a wall. And then one last row. This can be a wall. This can be a wall. This can be a wall. This is no wall, and this is a wall. I think it's fine. I mean, for a start, looks okay to me. And then somewhere in the middle here, the user will stand. The player will be put onto the map. Okay. So this is now the map. How do we visualize it? Ooh, we visualize it. We put the player somewhere. Where do we put the player? Player initial position is, or how do we map the map? We need to map the map. We need to map the map to the two-dimensional scene somehow. Or no, this is basically the source data. And then we need to derive from that source data an actual two-dimensional map, because every entry in that map is not just a single pixel. It might have to expand to, let's say, 50 pixels if we wanted to generate a two-dimensional map. Of course, we want a raycaster, but somehow I'm thinking of that we need to somehow transform this to something, right? This is not so trivial. But let's have a look at the tutorial. What is the next step? The user scans the area around himself. The user has a direction vector a direction vector. Depends on how you want to do it. I like to do it using angles, actually. So the map, and then where do we put the user? This is the map. Okay, I think we have a map. The map currently consists of a couple of dots, basically. We have a couple of data points. Now we need to expand the map or the model that we're working with to a two-dimensional map. This is just a 4x4 map, just for visualization. And some of these cells are filled and others aren't filled. So each cell in that map has a size, obviously. And since every cell here is a square, no, it's a cube, we want to model something three-dimensional, each side of each square or of each rectangle of each cell has the same size. So we need to define cell size here. Let's make it, I don't know what to pick for a start. Let's just make it 50. If it looks odd, then we will adapt it later. Okay. And now we need to somehow convert the map to a two-dimensional grid, I think, because we want to compute how the rays extending from the player intercept with these cells. Or am I thinking too complex right now? If I'm thinking weirdly, put it in the comments, please. I need some thinking hacks from you. Give me the one thinking hack that will improve my thinking by 50% for the rest of my life. And here, what strikes me as odd right now, or for a start, is that the player is not located right in the center of a cell. He's somehow off, of course, because the player can move at continuous steps. He can move continuously throughout the map. And here we have a cell size. Here we have a cell size. I think we need to scale up the map, or we need to... What do we need to do? This is crazy. Should we draw a grid? I'm thinking of whether we should generate such a grid first, because that would help us progress. But on the other hand, I'm not so sure about whether it will help us generate the 3D Terra at all. So, okay, let's say the following. The map must be is 5x5 right now. That's fine. Maybe it's easier if the map's dimensions somehow align with the width and height of the screen. No, but this doesn't really matter if we transform to 3D later. Okay, we need to define the player first. So struct player. Why do we need to define the player first? Because this is something that we can do right now without much thinking. The player has an X and a Y coordinate, and he has a field of view, angle, and the player has an angle at which he's currently looking. Look angle sounds weird. Face angle, camera angle. Or maybe the field of view can be a global constant. I mean, we can define the player field of view up here. So let's do that. Define player field of view. And let's say the player has a field of view of 90 degrees. I think that makes sense. How much field of view do I have? This would be 90 degrees. Yeah, maybe it's closer to 70 degrees. I don't know. 80 degrees. Let's put 80 degrees here. That was a very, very scientific investigation of human field of view. So that's the player's angle at which he's looking. Okay. And let's put that in a type definition, type def struct, and call that struct player here. Then I would say maybe let's draw the player. Let's just draw the player. We create a rectangle here. The player's just a rectangle, or even better, we create a dedicated method, draw player. We draw the player. First, we need to initialize the player somewhere. So the player, or the player can also be a global variable technically. Type def struct player. Oh god, what am I doing? Player equals. And since the player is just a struct, let's put the player. Let's put the player at coordinate 0, 0 maybe. How about that? Let's not overcomplicate it. And the angle at which the player is looking. What could be the angle? So what's currently going on is we have some kind of map. Let's say this is the map here. If we position the player here at 0, 0, and we give the player a direction into which to look based on this angle right here, this is the alpha angle, and we have some walls here, let's say these are some walls, then we should be able to start some interesting computations, right? So the player has a looking direction. The direction is, let's say, this is the angle. Or if we position the player here at the center of the game somewhere, then we could also measure the angle like this, like we did in school, which is somehow a bit more intuitive. Basically, it's just flipped. Yeah, we'll figure it out. Let's position the player at position 0 and have him look at a 45 degree angle. That sounds good, right? Because this one looks like 45 degrees. Oh my god, my thinking is so stupid, so slow, because this is a right angle. So the half of it must be 45 degrees. Okay. So we're progressing at microscopic steps here. Now, if the player looks at 45 degrees into the scene, looking from up there, then what happens next? Now the core idea is, again, the user or the player looks, and then we see when the ray extending from his eyes hits a wall. How do we know if it hits a wall? Well, we basically have to convert these values here to two-dimensional squares on the two-dimensional maps. We have a cell size, so let's create a real map of squares. How should we do it? We create a map. Well, basically this map already contains all the data, so I'm a bit disturbed by whether we have to generate another structure. No, actually we can just check if any of those rectangles is being looked at by the player. In this case, by the way, can we screenshot this? Screenshot. Then let me just copy this for you. Screenshot. Take a screenshot of this. This is now our map. Copying it into this thing right here. Where is it? There it is. Now, if the player is positioned here in the top left corner of the screen, let's use this color. This is the player. And the player looks down this line at a 45-degree angle. This is not neon enough. Down this line, then his gaze should hit right at this wall, which has value 1. Okay. This means we draw the player. No, we don't draw. Actually, we don't even need to draw. We could have two modes in the application. One is a 2D top-down mode, and the other one is the 3D mode. That would be very, very interesting. I think this would even make sense. So let's draw the player. The player, we draw him based on a new method, which we create up here, void draw player. We take as input the STL surface, P surface, and we take as input the player. Actually, we could take the player from the global context. It doesn't really matter. But definitely we will need to STL fill rect. We need to fill the rectangle on the surface based on the player's coordinates. Rect player rect is equal to, and the player is positioned at player.x, player.y. Here, player rect. And then down here, we update the window surface. That's fine. Let's see what happens if we compile this. Nothing works, of course. Error incompatible type for argument 1 of draw player. Ah, right. Because we draw the player onto a surface, of course. GCC, compile this. So we fill the rectangle now. And there's an error. Too few arguments to function as the fill rectangle. Why? What have I done? Did I? Oh, terminals. Good God. Never mind, let's just reset everything up. No time for that. Oh, it somehow worked. Okay, somehow recovered based on a magic keyboard shortcut. Okay, error to few arguments to function SDL fill rect. SDL fill rect, of course, takes also a color. Fill rect. The player has a player color. What color should the player have? The player should have a color player color. What is a nice neon green like this one? Can I see it here? Can I inspect this color palette? Oh. R. Let's make it this. G. B. I'm just guessing what a nice color could be. Okay. And what if we do this? Why is no player being drawn? Probably because... yeah, of course, the rectangle has no width and height. So let's do this. Okay, there is now a player in the top left corner. It's pink. I don't know why it's pink. Probably because I messed up the color definition here. This is R, G, B, A. Or is it a different color format? What if I do this? Still pink. What? Maybe this is a RGB format. RGB. Yeah, okay. This is now green. Okay, the top left corner is the player. This small rectangle there. Now, if the player looks somewhere, then what happens? We have a ray extending from the player's view. Let's have a look at the tutorial. So here this guy defines some camera plane. I'm not sure if that's maybe too much. It looks quite complex. The direction vector and the camera plane vector have the same length. The field of view will be 90 degrees. This guy defines a map. Oh, in the same way that I did it as well. Okay. Map width and map height. Okay. Then right. Okay. So currently we want the player to look somewhere. Let's make the player look somewhere. We draw the player ray, or we draw the grid. What do? We draw the grid on the piece surface based on the map. We draw the map, or we make the player look somewhere. My issue is that this is so simple. This map is so simple. How can we check if the player looks at any of those cells? We have to expand the cells. And this might be so simple to some of you guys. So sorry about this. The player looks at at a 45-degree angle somewhere. We can draw the ray. Let's just draw the ray. Draw ray on the STL surface P surface, but I don't know if this is getting us any closer to the goal if we just draw the ray. I mean, we don't have to draw any rays technically. We can just use our thinking powers to get closer to the solution. We don't have to visualize everything. I mean, we have awesome drawings here. So the player stands there, looks somewhere. How do we know if the ray... Well, we need a function we need a function. Let's just not think about how we define or how we derive a solution. Let's think about what we want to have. Get length to wall, or get distance. Get distance of, or until the next wall is being hit. We get the distance based on the player. Where is the player currently standing? Where is the player looking? And where is... Yeah, and what's the map, basically? The player, we don't store in the player where the player is looking. Oh, I have messed up the formatting up here. We don't store in the player where he's looking. We just... no, we are. The angle is the angle at which he's looking. And then the field of view opens up the angle. So we don't... How about we get the distance between the player and the wall, assuming the player looks at a certain angle. I will use double angle. This is a double. So a comma, a number with a comma. So this returns the distance to the next wall, assuming the player looks in given direction. And to be precise, again, the direction is usually a vector based on delta x and delta y. And we're using an angle. An angle is also a direction because the angle implicitly stores the delta x and delta y. We can derive the direction based on sine and cosine. I find angle quite neat. So returns the distance to the next wall, assuming the player looks in the given direction. How about that? Don't know if that's well formatted at all. And now we check the direction. Oh my god. So there are two ways to do it. We could scan the ray extending from the player's eye step by step as it's done here, or, because this is not really robust, you'd have to scan it at very small steps, otherwise you risk bypassing the cells here, and then the algorithm will think it never interfaced with a wall, because here, as you can see, the steps, they don't land inside any of the wall rectangles. So this is not ideal. There's another algorithm here that scans only along the sides of the squares, but this one looks quite hard for me. I don't know, I wouldn't know how to do it. So from the player's position, we get the next point on the side of any rectangle. No, I'm not sure how to do that, honestly. So how do we know when the next side of a cell in the game is being hit? Well, but okay, without thinking about the technical problem already, the big advantage of this is that here we always detect all squares. We always detect all walls because we never go past the wall, because we scan all the walls on all the cells of the game. As you can see on the image above, the ray hits the wall exactly where we want it in the way presented in this tutorial. An algorithm is used that's based on DDA, or digital differential analysis. Oh no, this sounds so scary. DDA is a fast algorithm typically used on square grids to find which squares a line hits. For example, to draw a line on a screen, which is a grid of square pixels. So we can also use it to find which squares of the map our ray hits, and stop the algorithm once a square that is a wall is hit. Yeah, but how? Modulo something maybe? Some ray tracers work with Euclidean angles to represent the direction of the player in the race. Yeah, that's what we're doing, Euclidean angles in degrees. And determine the field of view with another angle. I found, however, that it's much easier to work with vectors and a camera instead. The position of the player is always a vector, but now we make the direction a vector as well. This is so complex. Is there no simpler way? Probably this is the nicest way, but I'm really curious about this DDA thing. In the next code piece, more variables are declared and calculated. These have relevance to the DDA algorithm. So we need for, what is that? Side distance x, delta distance x. Here is 1. Delta distance y here. Oh, this is not trivial at all. The DDA algorithm will always jump exactly 1 square each loop. Either a square in the x direction or a square in the y direction. What does he mean with 1 square? Yeah, of course. 1 cell here. If it has to go in the negative or positive x direction, and the negative or positive y direction will depend on the direction of the ray, and this fact will be stored in step x and step y. Those variables are always either -1 or 1. But then I'm wondering, if we move at exactly these intervals here, then how do we know that we hit the rectangle? Because here we have the risk of a floating point imprecision. So this is very, very weird. Wait a second. My phone just turned on by itself. No idea why. Okay, never mind. And this is infinite precision. No, yes it is. This is infinite precision from the player. Well, okay. I'm wondering, if we have the player standing here, and let's say this is the grid. This right here is the grid. Dun, dun. Oh no, this is a bad example. Let's make the grid like this. This. Dun, 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 dun. And now we create a ray. Let's say the ray is this. Then how do we know that This right here is a relevant point, and this one. This I don't get. This one seems a bit more natural because here we move along the width of a single cell. But this one, what the hell? And we move based on the angle, that's fine. I don't know, guys. DDA algorithm raycasting. Let's have a look. The DDA algorithm explained interactively. I've written a number of voxel ray tracers, and all of the good ones at least, use the digital differential analyzer algorithm for raycasting. I've only ever implemented this algorithm once by copying a reference somewhere. Since then I've used and reused that code, but I have something to admit, I've never really understood how it works. This is horrible, guys. So, yes, okay, this is the player. Why is it called RO? And this is the viewing angle. This is nice, okay. This makes sense. Now, this is the cell the player's in, right? This makes sense. And this is the viewing angle. Makes sense. Now this is where it gets interesting. But I find this super complex for a simple project here. And these are the points that we are looking for. Let's have a look. If we rotate this angle here, you can see that whenever we intersect... Is there a bug in this? Whenever we intersect with a line, there's supposed to be another circle drawn here. Like this. Okay, we get the distance from the player. I don't know. This is so weird. This is so weird. Now, come on. We'll use the simple approach. I mean, if we want to optimize it, we can just do it in the get distance player method then. Ray unit step size, ray length. Draw grid space. I will do it much simpler, guys. I'm not capable of that. Or maybe I'm capable of it. I don't have the time for that. I want to have the base principle. I want to understand the base principle of all of that, what we're doing. Don't need to go into so much detail and optimize everything. So here we get the distance from the player to the next wall. But somehow this feels not right. Raycasting DDA. The digital differential analyzer algorithm adapted to 3D is exactly the thing one needs to travel along a line through a grid of voxels. I feel like I have to do this algorithm, otherwise I feel like a cheater. But I like the other approach a lot, actually. As you can see on the image above, the ray hits the wall exactly where we want it in the way presented in this tutorial. An algorithm is used that's based on DDA. DDA is a fast algorithm typically used on square grids to find which squares a line hits. Holy crap. No, forget it. I'm not going to do it. It's way too stupid for me. Let's keep it simple, guys. So we look in some direction. What's the grid even? The grid. What's the grid? And then we look in some direction. How do we intersect with this map, with the walls on this map? I really feel underqualified today. Get distance. Nothing SDL. We get the player's X coordinate. Flow, no, double. Maybe the player should have a double coordinate here. Double coordinate and angle, just for precision. Then we get no. We cast a ray. Okay, we cast a ray. That's the heart of the project that we're doing. We want to cast a ray. We don't want to deal with these weird optimizations. First of all, the first and foremost thing that we want to do is we want to cast a ray, starting from the player's X and Y position. We cast a ray until a wall is hit. Oh, now my brain turned on again. Okay, so while wall detected is false, and wall detected is a Boolean. Wall detected that is initially false, while we have no wall detected, so we can do not wall detected like this. We cast a ray from the starting position, double start X equals player X, so we start from the player's X position, and start Y equals player Y. And maybe we need to rename this to X or ray X and ray Y. And then inside here, we check, is the ray inside a wall? If the ray X is bigger than what? Okay, now it's getting weird, because now we have to somehow convert the cells to our ray coordinates. If the ray X is bigger than no. First of all, we need to ask which cell is the ray inside now. Which cell is it inside right now? So, and for that we need to consider the cell size and the map size. The map is currently a square. Map size. the map is an array of map width by map height, I think, or was it height by width? Let's just keep it for now. Which cell is the array inside right now? We need to define map width equals 5, just like map height equals 5. And here we need to check map width multiplied by cell size. This is the total size of the map. And maybe we need to even check, is the ray even inside the map right now? Because if it's outside, we don't even need to bother. If ray x is smaller than 0, or ray x is bigger than the map width multiplied by the cell size, then we return. No, then we don't return. Then the distance that we get, the distance must be a double, is, let's say, negative. Because there's nothing we're looking at. Ah no, wait, this means that the player, if the player is outside the map and looks inside the map, he can't see anything anymore. No, this doesn't make any sense. Which cell is the ray inside now? Ray x bigger than map width multiplied by cell size. What if we do total map size, or we do ray x is bigger than map width? No, I don't like this. Which cell is the ray inside right now? Ray x. Ah, of course, ray x modulo, no, divided by map width multiplied by cell size. So map width or scene width maybe is even better. Scene width is equal to map width multiplied by cell size. Scene width. This returns a number, and if we cast it to an integer, then it should return the number of the cell. Because if ray x is 0 and we divide it by anything, then the result will be cell number 0, which makes sense. And if ray x is 900, or no, if it's the end of the scene basically, in our case it's 500. No, 250 even only. Then it will tell us that the cell x coordinate is equal to, well, the last cell basically. I think this might work. And the y coordinate for the cell is ray y divided by scene height. And then we can check if the map at this position, oh, now it's getting interesting. Cell y, cell x is true. Then we know that we hit a wall. Then wall detected is true. Now we just need to make sure that the map is accessed properly. So maybe, what is the width here? We have an array of arrays. Let's assume those are rows. Then the first property, I never get which one comes first. Map width or map height? Let's map width. I remember in the past it was always height first and then width. I never really get intuitively why. But okay. Now we have detected a wall. Then we need to we don't even need to do anything. We can just... no. Okay, let's return the distance, the ray distance. The ray distance is a new variable that we need to create. Oh, what happened? Oh my god. The ray distance is a new variable that we need to create. So here, is the ray inside a wall? If yes, we return the ray distance. Okay, that's great. Ray distance is at first 0. And it's also a double. And else we increment the ray distance by No. We don't need a separate variable, actually. We just need the ray x and the ray y. And then we can derive the distance from ray x and ray y. The distance in that case would be the square root of... Let's have a look at the square root definition in Siemens squared. Takes as input a double. Okay, that's fine. That's what I wanted to make sure. Power of ray x minus player x. That to the power of 2 plus power of, and then same for y, player y, power of 2, and that should be the distance that we found. But first we have to move the x and y coordinates along this angle. So cell x, no, ray x, the current position on the ray. And by the way, just to be clear, the ray x and ray y that we're talking about are these dots, these red dots here along the line. And the x position always increments according to sine of the angle. I'm not so sure. The sine of the angle. We have an angle. At first it's 0. At 0, the sine is also 0. Yeah, okay, that makes sense. Let me just draw it for you. So we have a position. Let's say this is the position right here. Now we have an angle. Let's say this is the angle, alpha. And we want to move along that angle. Let's just simplify the case. If the angle is 90 degrees, let's say this, then there will be, then the next point that we scan will be, for example, here. This means the y component has increased, but the x component stayed the same. Okay? This means that at angle 90, we increase y, but we don't increase x. And at angle 0, let's say alpha is equal to 0, we increase only x. This means if we look at the trigonometric functions, cosine and sine, sine looks like this. At angle 0, this right here is value 0, sine has value 0, but cosine has value 1 at this position. Well, this is the 1. So at angle 0, x increments according to cosine. Cosine of the angle multiplied by step size. Ray, step size. And x and y, I mean, increments according to sine, because only at 90 degrees angles sine is not 0. And actually, if we now want the angle to be counted upwards, so let's say this is the angle right here, this is a positive angle in our normal mathematics sense. So here this is upwards. Then we need to do minus sine here probably, because in screen coordinates, those are the coordinates. Y faces down, x faces right. Okay, so if you had a normal angle here, then this would be measured like this. Alpha would be measured down. This would be the opening angle here. Maybe we want an angle like this that opens upwards and counts like this. I'm not sure about that. No, but earlier we defined the player angle to be 45 degrees and it was facing downwards, so that was fine. So we are aligned with the screen coordinates. Now this obviously doesn't compile. We need to do stuff later, and we need to define the ray step size, of course. Define ray step size, and let's make this a super small number, or a super small number. Yeah, a rather small number. And then we will see how fast it is. And there's still an error boolean. I wrote boolean somewhere. This is of course not something that we should do in C, because boolean doesn't exist, but bool does. So now let's compile. Scene height is undeclared. Scene width, scene height. Scene width is this. Scene height, we have to declare it first. Height is equal to map height multiplied by cell size. Okay, let's compile and execute. Unused variable counter. Okay, that's good. Get distance. Warning, control reaches end of non-void function. Okay. Counter can be deleted. Oops. Draw player worked before. I remember that. If we do this now, right, one more issue. We have to also link math libraries. So let's append -lm. Okay, now the application starts. We have the player still in the top left corner. Great progress that we did so far. Now we need to do, as a next step, right, the void return return type was wrong. I know it was fine. What's the warning here about? Control reaches end of non-void function in get distance. Ah, okay, that means we forgot to return something somewhere. While no wall is detected, we do something. Then at some point we return the distance from the wall. If we have detected a wall, that's fine. Else we move along the ray even more. And then I would say we need to do some emergency saving thing that saves us from an infinite loop. So how or when do we exit? How far do we scan? Right, if we can do that here actually. Should we compute the distance all the time? Currently the distance from the player? Because if we compute the distance all the time, then we can say, for example, we have a render distance. Oh, that's nice. A render distance that we allow. So if the distance or ray distance is bigger than the render distance, which we define in a second, if the distance is bigger than the render distance, then we return, what do we return? -1. And this right here is the ray distance, which we compute here. Double ray distance is equal to this. But still, this function has no real return value here. So if nothing is returned and somehow the loop exits, which should never happen, then we return. And actually we can crash the application. We can crash the application here, printf. What the hell happened? Exit with a negative error code. And return, but this will never reach this return code. Let's define a render distance. Oh my god, this is such nice quality code. Render distance. Render distance is, let's say, what could it be? 1000. I'm just guessing numbers here. And okay, we are drawing the player. We are not yet getting any ray distance. So let's see what happens here. Get distance. Double distance equals get distance from the player at a 45-degree angle. Okay. Let's see where this is called. Up here, player double angle. Okay. And then we need to print this variable here, printf got distance. F or D? F. I think it was F for a floating point number. Distance like this. And let's see what happens when we compute. We got a distance 0.5. What? This is an odd value somehow. It's not a real error, but it also doesn't feel like it's a real distance. So somehow it feels wrong. Player X, ray X. Ray distance. If the ray distance is bigger than the render distance, we return this. Else we check which cell is the ray inside now. Oh, and then here we have to be careful not to access the ray outside of the scene. So if the cell X is bigger than this scene of the, no, it's bigger than the map width, then, or the cell Y is bigger than, maybe bigger than or equal to, the map height, then we need to exit. So here this is returning God distance all the time. Somehow it's weird. What happens if I move the player? Does the distance change? Let's try that. Player.x plus 0.01. Same for y. So this means the player is moving toward the wall he's looking at. Remember, the player is located here in the top left corner and now moves toward the wall because we're incrementing both x and y. This means that the distance should shorten. And this looks so weird. No. This is definitely wrong. So what's going on? Wall detected, got distance -1. If the cell X, cell Y. Cell X, we have to divide the scene width, I think. Scene width by ray X instead of the other way around. Scene width divided by ray Y, like this. Segmentation fault, oh no. Of course, scene width divided by ray X and scene height by ray X. No, ray Y, scene height. Segmentation fault. So now we check, is cell X bigger than or equal to the map width? Maybe we can check here what these values are by putting a printf. Cell values are D and D. Cell X and cell Y. Okay, what the hell? Cell values are those. Okay, that's completely wrong. But why? Scene? What? What if we printf here, ray chords r x equals some floating point number and y equals another floating point number, ray x and ray y. Let's see what happens. Okay, the ray coordinates definitely start at 0, which is good. Why are the scene the cell values so weird? What's the scene width even? Of course, I'm dividing by 0. Why am I doing that? Why am I doing that even, guys? What the hell am I doing here? No, I need to invert that. Ray x divided by scene width. and ray y divided by scene height. Okay, now it looks like the ray's coordinates are incrementing and the cell values are incrementing as well. Perfect. Okay, it looks like it's working as I expected, and somehow the player... right, the player is moving. Okay. And we always get a distance of -1, so that's definitely wrong. The player's moving, and so something is still not correct. I'm wondering which of those -1 cases we enter. Is the ray inside a wall? Map Y, cell X. Wall detected is 1, and we return the ray distance. Otherwise we do this. We never enter the what the hell happened clause. That's good. This is the distance. That should be properly computed, but we can also print f it. Ray distance equals this. Let's see. So the ray distance seems to be always 0 at this point. So it looks like we're prematurely exiting the application. But of course the ray always starts at the player, but then it should move toward the next cell. So here we are getting the cell coordinates. Wait, let's have a look at the logs here. Let's just restart this and let's cancel quickly. What happens, because we have a map of only 5 by 5 cells. So technically, right, the first cells, they even work. Here the ray distance, oops. The first cells seem to work, at least in part. There's some distance calculated here. There's some distance calculated here. And once he reaches this position, the distance is 0. Okay. Don't know about that exactly. These are the ray coordinates. Cell values are 4 and 4. But why? No, something doesn't make sense here. Why are the ray coordinates so small and the cell values are so big already? So this is ray... because we have to multiply this by the cell... No, we don't have to. This is the cell identifier. And the ray x is a small number. We divide it by the scene width. No, this doesn't make sense somehow. We divide it by... No, actually, we should divide ray x by the cell size. Same for ray y, cell size. Let's see what happens now. Okay. Cell values. Okay, this here the ray distance is 233. Cell values are 2 and 3. Okay, could make sense. Yeah, why not? Okay, I see no large inconsistency now. We get some reasonable distance values. That's fine. Maybe it works. I have no idea. what I would like to do now is, let's try to visualize the player looking in some direction. So currently the player is looking in this direction at a 45-degree angle, but we need to draw scene in front of, or in field of view, or draw the field of view onto the surface from the player. The player has some angle at which he looks, right? We can remove all of those things. And then in addition, we need to, oh, maybe that's even it. We draw the field of view. Let's see. Void draw field of view. How does the field of view drawing work? We have a player. No, we have an STL surface. We have a player. And the player looks somewhere. The player looks at multiple angles. Basically, what's happening is we draw vertical walls depending where the player looks. So we need to loop over something. Let's say for int I, and until when do we loop? We loop until which count? What's the count, guys? Field of view. Actually, we should have a sample size, maybe. And maybe we don't. Let's just delete all of that. Maybe we have a double angle that starts at the player angle minus field of view. What's the constant? Constant player field of view divided by 2. So we have the player looking. This is the player. And the player looks in some direction. Let's say this is the angle, and then this is the field of view. And as you can see, this is the field of view divided by 2. This is the leftmost portion. So basically angle minus field of view, and an angle field of view plus field of view divided by 2. So basically we have a rotating angle over the field of view. So here for the angle player, angle minus player field of view, until angle is, no, while the angle is smaller than or equal to player angle plus player field of view, like this, we increment the angle by some very small number. Let's say 0.1. And for each angle the player is looking at, we check the distance. Check distance for every angle in field of view. How do we do it? We check the angles inside the field of view. We do brain shut off. Sorry guys, my brain is shut off. Attention, attention, alarm, alarm. We have a function for that. Get distance for the player looking at the current angle. However, the distance function here expects the angle in radians, because down here we use radians for this computation. So radians, player looks in given direction, angle in radians. And here we have defined the player angle and the player field of view in degrees. I know there's a constant in Raylib in C that converts radians to, or degrees to radians. Or we can just derive it ourselves, it really doesn't matter, it's not too hard. Convert, let's check, convert degrees to radians. Okay, we 1 degree, we basically multiply by pi divided by 180. Right, because 2 pi is a full rotation in radians and 360 is a full rotation in degrees, so pi divided by 180 is that conversion. But I like 2 pi divided by 360 more because it's more explicit. We can define our own degree to radians here, and it's basically pi divided by 180. Okay, so we get the distance angle multiplied by, or should we consider all the angles radians here as well? But then this increment would be way too small. Let's try with dec to rad just like this. And this, we need to fix up here the notation, p surface, just like this. We get the distance, double distance, and based on the distance, we draw a line that is centered along the horizontal center axis of the window. Based on distance, draw a line. Based on the distance, draw a line. Based on the distance, draw a line. We have the distance, now we draw a line. We draw a vertical line. Void, draw vertical line. On the SDL surface, P surface, player. No, we don't need the player, we just need this, or we need the height. Draws a vertical line centered around the horizontal center axis of the window. Okay, now we draw a vertical line, and we can draw a line, as you know, using an STL rectangle, vertical rect, that has a starting point x. Oh, we need to know the coordinate. Basically, we need to know along the screen. Let's say this is the screen here, or the window, and we want to draw vertical lines around this center line, and the vertical lines will be like this, depending on the raycaster result. Oh God. So we need to know The only difference between those lines is basically the x position here on this axis. So we need to know double height and double x position. So basically we can draw two rectangles, one extending up, one extending down. Ah no, but rectangles in STL always have a starting x and y position at this, which is the top left corner, so we need to derive it. Okay, the x position is the given x. The y position is the center. Y position, height divided by 2, minus the given height divided by 2. Then the x expansion, how wide a single vertical line is. Let's just put it at 2 or even 1. Let's make it 1. So basically we have a 1 pixel wide vertical line, and the height of that line, the total height, is height. And then we do STL fill rect on the surface. We use the vertical rect we have just defined, and we need to pass a color here. So let's pass a UN32 color. Colors in STL are UN32s. And where that method is called, here we call this first piece surface height. Let's just make the distance equal to the height. No, we need to inverse it. 1 divided by distance. Or is that a weird projection? Let's just do 1 divided by distance. I mean, 1 divided by distance is effectively zooming in. Well, if something is close to my head, then it's very big. If it's far away, then it's small from my perspective of view. And the next step is to pass the height. No, the height we have already passed. The x position. The x position. Oh, the x position. That's also interesting because the player always has a field of view. The leftmost angle needs to be x0. So the current angle is, oh, we need to somehow convert the field of view to the screen coordinates. Wait, let's try to do that. Double starting x is player angle minus player field of view divided by 2. Starting y, player angle field of view divided by 2. No, not starting y. We don't need to do anything along the y-axis. We need to define an end x or end display x, something like that, plus player field divided by 2. Both of those have a difference, and the difference is the player field of view, of course. And then we need to scale the field of view to. All right, we need a scale. Forget about all of that. The scale is the player field of view divided by the screen size, or rather the width of the screen divided by the player field of view. So how many field of views? No, how much bigger is the width compared to the screen of view field of view? And then we scale. So we need to pass here distance angle, distance angle height x X is scale multiplied by angle, or rather angle multiplied by scale. This scales any angle from 0. No, doesn't do that. Any angle is multiplied by scale, and then we need to offset it somehow. The angle could be anything. It could be 78 degrees to whatever, 88 degrees, 78 degrees to 150 degrees. So the lowest angle should be the offset plus offset angle multiplied by scale plus offset double offset is equal to player angle minus player field of view divided by 2, I think. And then we need to pass the color. Let's just pass white. I think some colors are predefined in STL, aren't they? Let's check STL colors. Are there predefined colors? I don't really remember. There's a structure STL color. Let's check here. Tab E, STL. Was there anything about colors? No, nothing. Misc. White. Color. No idea. Okay, let's just use our own defined color white. Color white. And now let's fix some errors. Okay. There's a typo, first of all. Field of view it is. Now, let's fix the next one. Vertical rect is an STL rect, incompatible type for argument 2 of STL fill rect. What does that mean? Ah, I know it. It's because fill rect only accepts addresses. So let's search for the vertical rect here. And here we need to prefix the address. And then, let's see. There are not so many errors anymore. So there's a payer FOV. It's also nice, payer. Let's search for that. Replace it with player FOV. And now, in function drawer field of view, error pi is undeclared. Oh, I think pi is coming from math.h, but it's mpi or m_pi. Let's see if that fixes it. And yes, that fixes it. Let's just clean up the screen a bit and show you the remaining error. Error too many arguments to function draw vertical line. Draw vertical, yeah, okay. Why? Let's check. So currently the function accepts the height, x, and color. I am passing into it the angle. The angle is of course not desired. Right. And let's just make everything explicit here. Visual height double. Visual height is 1 divided by distance. Then the x coordinate of, oh my god, vertical line is equal to angle multiplied by scale plus offset. And then the color we can leave it in. Visual height, x coordinate of vertical line is this. And let's try to compile and execute. And nothing is visible. What if we close this? At least we don't get any errors. Oh, we can't close it. Sending a couple of Control C's here to try to interrupt this. Oh my god. Come on. Or I'll use magic powers. Raycaster kill -9 75873. Oh. 75873. I had already closed. Okay. So here, I'm drawing the player. I'm drawing a field of view. What's currently missing? Obviously, something is being computed here. Cell values are a bit odd. Why are they all -1 and 2? That's weird. But okay, the player's not moving. But the player should be positioned at 0 and... Ah, okay, but those are the cell values of the ray. So what are we doing? We are currently drawing a player, and then we're drawing a field of view. We're drawing the entire field of view of the player for every single angle. Yeah, it's quite a lot of computation. And then for every result, for every distance that we compute, we draw a vertical line. That's how I understood raycasting at large. So there's some issue here. We fill a rectangle at the x-coordinate. Y-coordinate is height -2 minus height divided by 2 minus height divided by 2. Width is this, height is this. Okay. Then we're drawing it here on the surface. One issue could be that, of course, after every iteration, we need to update the window surface, delay, and then before we draw anything else, we can reset the screen by doing SDL update window surface or SDL fill rect and then doing null. I think that was a hack to flush the screen in SDL. SDL fill rect null. Let's have a look. Yeah, null to fill the entire surface. Okay. And now let's just roughen up our computation a bit such that it is faster. What's the current ray step size? It's probably very, very small, right? Let's increase that a bit. The render distance doesn't need to be 1000. Let's just make it 250 and let's see what happens now. SDL fill rect null, too few arguments to function. SDL fill rect, oh great. Okay, so what did I just look up here? Null. Or null to fill the entire surface. Right. Ah, yeah, okay. We of course need to specify the surface that we want to fill. P surface, null, and then color black. So up here, let's define color white and color black. Oh, of course I need to call it color black here. And now let's see. So we still have an unclosable application somehow. I don't get why it's not closing, why it's so reluctant to close. 76141. Okay, now it's closed. Cell values are -1 and 2. That's definitely wrong. But the ray distance is always computed to something, so that's okay. But overall, that's not the distance that's being returned. Ray distance is this We need to print it when it's being returned. That's when it's meaningful. Let's check. It's never returned. Let's check this log here. Cell values seem to change, so somehow the rays are moving. Why is x -1? So somehow the angle is completely skewed. Why? Ray x is cosine angle multiplied by ray step size. Ray y is sine angle multiplied by ray step size. That's completely weird. Let's see here if we ever receive a reasonable distance. Distance equals f distance I don't think it returns so much good. Occasionally it does return a distance. Okay. So we definitely don't need to log the cell for every single computation or for every single loop. This we don't really need, but still the cell values are very odd to me. Why are they becoming negative? This only happens if x starts becoming negative because the cell size is positive. And ray is incremented by the cosine of the angle multiplied by ray step size. Somehow this... Where's the negative value coming from? I don't get it. This is impossible. Ray x divided by cell size yields a negative value. How about we log the cell values and then also the ray values x and y. Ray x and ray y here. Oh, I think there was a warning. And we should always see the warnings. And that's what I meant earlier by it's risky to concatenate the execution and the compilation because you want to see the warnings before executing anything, because the warnings are super, super valuable. 76306. Okay, it's already cancelled. Okay, these are just warnings about printf. F and F here. And this compiles without a warning, and if we execute it, this is horrible. 76361. Ray values are x equals this, then x is incremented, then y is incremented as well. Cell values are this. This makes sense. Yeah, this is correct. This is overall correct. But here there's no example of negative. Well, of course, depending on the field of view, the negative values make sense, because at the beginning of a loop, the player stands here. In this corner, he has a field of view. Well, he has a view direction of this, but a field of view that's like this. So it can be possible that cell values are... No, he doesn't have a field of view like this. He has a field of view like this. So what's going on here? So maybe the for loop here is broken. The starting angle is the player angle minus the player field of view divided by 2. That's fine. While the angle is incremented, no, while the angle is smaller than the player angle. Oh my god, what's that? Smaller than the player angle plus player field of view. Let's just make it explicitly belonging together. And let's ensure the precedence here using parentheses. The angle is incremented by 0.1. Okay. Then we get a distance here. Probably maybe it's some degrees to radians thing, and it just started something I didn't want to start. So this is really doing way too many computations, it seems. Or I think, I'm not 100% sure. So here we fill the rectangle with nothing. We don't need to draw the player anymore because the player is located. We draw the 3D scene right now. We update the window surface down here after drawing the field of view, and then we delay by 10 seconds. Yeah. Scale is width divided by player field of view. Okay. How is the scale applied down here? Angle multiplied by scale plus offset. Or, what about angle minus offset multiplied by scale? No, that's wrong. Offsets are never multiplied and scaled. Or are they? Angle? Okay, I'll just try it and see what happens. Nothing. But I will change the view to be a lot more a lot rougher now, because I don't have the patience to wait for these weird exits all the time. And maybe I should reduce the render distance as well, but how am I properly exiting for the render distance here? If the ray distance is bigger than the render distance, then we return -1. Okay, we return -1. If the distance is -1, then we just continue, I think. We should do if the distance is smaller than 0, then the distance calculation went wrong or out of render distance. This means we just continue the loop. We skip the iteration. Maybe this changes anything. No. We have to check whether it's smaller than 0 or equal to 0. We can't divide by 0. And then additionally, let's just increase the angles by something else. Oh, well, I convert degrees to radians here. So here I assume that the angle is in degrees. And up here, it's something else. It's in radians. But maybe I should just do it here. Multiplied by deg to radians, degrees to radians. Angle. And then we can check. We could technically check which angles are currently being scanned. This would be quite valuable in my opinion. Or we can take this as an opportunity to jump into a debugger. GDB. Or let's compile this. Oh, error. If the distance is smaller than or equal to 0. All right, I forgot the semicolon here. GDB raycaster. Let's compile first. GDB raycaster layout source. Okay. I would say we put a debug breakpoint in line 108 and run. Refresh here, and now let's check. Oh god. Refresh. So, what's the distance? Distance is this. Okay, fine, could be. What is the angle? 5. Makes sense because the... Right, that makes sense because the angle that the player is looking at is 45 degrees. And that means the angle starts at 5 because the field of view is 80. Then there are a couple of things here. Refresh to clear up everything. How can I step into it? Step. Okay, refresh. Ray distance. Let's print the ray distance here. 0, okay. Print cell X. Print cell Y. It's all fine. Refresh. Whenever we have a print F, then it breaks the layout of the debugger, so we need to refresh here. And then we increment. Print ray X. Print ray Y. Yeah, it's okay. For me, it looks okay, to be honest. So let's compile. Is anything weird in my configuration? The render distance is maybe okay. The ray step size could be larger. Let's just make it 1. Maybe it changes anything. Maybe the application quits now. If we want. It quits at least a bit faster. But still nothing is visualized, and that's bothering me. So when we draw the field of view, why is nothing ever been drawn? That's weird. Let's printf drew rectangle, and let's put here the 4 properties of the rectangle and see if any of those are odd. X, vertical rect X, vertical rect Y, vertical rect width, and vertical rect height. Let's quit this. I don't see any logs ever drawing any rectangles. Here. Drew rectangle. Add coordinate 1013. That's the x coordinate. No, that's completely outside of the window. So maybe that's the issue. And also, the height was 0. Wait. Drew rectangle. The width is 1. The height was 0. Why is the height 0? Because this is probably a floating, not a floating point computation. Wait, what happens if I do this now and quit? The distance must be a double, right? The distance is a double. Yes. Drew. That's weird. Did I even compile right now? Let's see what happens now. Drew a rectangle. At this coordinate, width and height. Why is the height 0? Printf. Let's printf. Oh no, we don't even need to print it. It's weird. X, Y, height. What if I replace the height just to make sure by, let's say, 50? Maybe I'm messing something up. Oh, and now there's something happening at least. That's a good sign. And that could be the walls that we have defined. So we see walls, space, and walls. Does that match anything from here? Walls on the left-hand side from the viewer's perspective, space and walls. I think we are approaching, guys, a working raycaster. Those were the walls we saw, and that is a wall we saw. Okay. Oh. Okay. Okay, now it's getting interesting. So why is the height 0? This is an issue. The issue is probably that we divide 1 with the distance. This yields a way too small result, and we need to scale, vertical scale this up again. So let's define vertical scale as 300. Or no, let's define it as the height of the screen. And let's go here and see what happens now. That's interesting, guys. That's so interesting. Okay. we are dividing 1 by the distance. What if we divide vertical scale by the distance directly? Does that make a difference? So because if the distance is 600, then it will be just a single pixel. If the distance is smaller than that, for example 1, then it will fill the entire screen. But that's not really... It's kind of doing some scaling here, but it's very, very small. I don't know why it's so small. The height, I mean, is 600. What if I do height multiplied by 10? Let's see if this changes the output in any way. Oh God, guys. Okay, that's awesome. That's awesome, guys. We are approaching something that looks like it could be a proper raycaster. Of course, not using the perfect, using the best possible algorithm, but this is nice. Why is the scale required to be so weird? Scale. Let's search for scale. Vertical scale divided by distance. Vertical scale. Okay, I just put vertical scale 100. That's probably too large. Or let's make it 50 instead of 10. Put it in the comments if you know, guys. Wow, this looks nice. Holy crap. This is exactly the way, this is exactly the map that we have defined here, I think. So on the right hand side, we see this thing. On the left hand side, we see this. Right, we have some empty space here, right? That's this part. This part is an empty space, and then there's this corner here, which is what we're seeing here. All right, guys, this is so awesome. Now, let's remove the lock here to improve the performance a bit. Let's make the angles a bit finer. Okay, I actually liked the way it was displayed with lines before, so let's just keep it that way. I know it's not ideal, but somehow I like the raw nature of it. It just looks nice. And let's make the player move when we press a button. If this works, I'll freak out, guys. Because then that's the foundation. That's the foundation that we wanted to have. So we need to check SDL events. Let me just close a couple of applications here. Yeah. SDL key press, arrow key. Right. We need to check for SDL, for an SDL key event, SDL key event. SDL keyboard event, probably. SDL2 keyboard event. Right, there it is. So SDL key down. We want to check for key down. Key down. In case the user presses a key, and here we can do handle key or something, I don't know, handle key event, break. And then let's define a function here, void handle key event, no, SDL event. And then we need to check which kind of key was pressed, using the key symbol. So let's access SDL. Let's just check the event again. So an SDL event has a type and in addition, if it's that type, you can access one of those event sub-objects here, and we will need to check for the event type keyboard event here, key. So we need to access the key. So event.key, and then we check here the type, no, the key symbol, the key that was pressed or released. .key sim. This is a SDL key sim object. Let's see if we can get it here somewhere. Tab E, just like this. Let's vim grab for SDL key sim. Was it that? No, key sim in all.h files. Vim grab SDL key sim in all.h files. No match. No idea where it's getting those from. Keyboard key sim. There it is. I don't know why I didn't find it. Maybe I messed up the vim grab command here. Okay, so a key symbol has a scan code. This is the physical key scan code, or a virtual key code, which is the SDL key code here, sim. So I would say we can access keysim.sim. I know the syntax is very weird, or the object structure here is kind of weird, but it is how it is. And then let's find the damn keyboard key code, SDL key code. See SDL key code for, yeah, I think online is a bit faster. SDL key code, here it is. And then there are SDL keys. Let me show you how to use them. So if the key code, basically this is the key code, wait, let's put it on the stack. SDL key code equals, or code equals this. If the code is equal to SDL K, and then there are a couple of key codes available here. For example, all those numpads thingies here. There should be an arrow key somewhere. SDLK. Up, right, up, left, down, right. So up, then if the user, what do we want to do? We want the user to be able to rotate his field of view. We can do that using the left or right arrow keys. So SDLK left, then the user, the player dot angle will decrement by, let's say, 0.1. If the code is SDLK right, then the player angle will increment by 0.1. If the code is SDLK up, then the player will move forward. Moving forward means the x coordinate increments by, and now this depends on the angle. We already learned that cosine of player dot angle and now the player dot angle is degrees. We need to convert it to radians. Oh god. Cosine of oh god, this is the part that I will mess up again. Player dot angle. Let's put another constant here. Rad to degrees, and that is probably just 180 by divided by m pi multiplied by rad to, no, degrees to radians. Ah, we don't need another constant here. We just convert degrees to radians all the time. Multiplied by, and then the step size is basically 0.1. That's basically the speed, player speed. We can define player rotation speed. Let's make it 1, and player movement speed, let's say 10, I don't know, or 5. Okay, the player angle increments by player rotation speed. The player angle increments by player rotation speed here. The movement increments by player movement speed, like this. Same for SDL key. Ah no, of course we forgot, or I forgot the y coordinate. The y coordinate is this increments by the sine of the player angle multiplied by the movement speed, degrees to radians, fine. Okay, and then we can basically just copy this for SDL key down, and that's basically the same thing, except we need to change this for a decrement operation. And I think if that works, I'll freak out. Okay, that's a working raycaster so far. I press the left key now, and it's working, guys. It's quite slow because, oh my god, this is so nice. Guys, this is crazy. This is crazy. I need to increment this, or I somehow need to improve the speed a bit. Holy crap, I didn't expect to finish that at all. Let's just find another printf statement that I can remove because they are always annoying as hell. So, and what do we need to adapt? We need to adapt. Well, one more thing that we could do is, depending on the value here of the cells, we could color them differently. For example, here, those can have a different color value because they are 2. This can have a third value. Let's define a couple of other colors here. Color blue is equal to 0x00 or ff00 RGB or something. I'm just guessing. And then color green, color red, maybe red, or yellow. Wait. Color UN32 SDL. We can, of course, also dynamically compute colors using the pixel format. Get RGB values from pixel in the specified format. No, that's not what we want. Convert surface. No. Get RGBA. Maybe that's something. No, but not exactly. Never mind, let's not deal so much with colors here. FF, color red, 0x, FF, 0000. I think that could be red. And okay. So where do we color the current, where do we color the lines? The vertical lines. Here, fill rectangle, vertical line, and we give it a color. When we draw the vertical line, we pass it just color white down here. Color white. We don't want that, maybe. Color, but get distance doesn't tell us which kind of rectangle, or which kind of box the ray interferes with. So we could make get distance return a structure that we define. Let's just do it. Type def struct double distance and int box type. And we call that structure a distance result. And that distance result is, let's put some documentation here, tells us which, tells us the distance and type of box the ray collided with. Okay. Now, down here, we don't get the distance, but we get a distance result. Results here. And instead of using the distance here, we get the results.distance. Perfect. And the color can be determined from dynamically from the result. So when we draw the vertical line, we draw, get the color, maybe, or let's just dynamically compute it here. Probably not so nice, but okay. If result.box type equals 1, then color, no, let's do it differently. Switch. So we switch over the result box type, and then in case the result, or in case it's 1, then color is color white, break. In case it's 2, then the color is color blue. And in case it's 3, then the color is color red. Maybe it works. I hope at least. Let's pass the color down here. And let's see. Guys, if this project really works out, this is a major milestone on this channel, in my opinion, because this is really an upgrade in the kind of projects I have done so far. By the way, I have no, forget about it. Error expected parenthesis before numeric constant. Okay, there's a parenthesis error in line 35. Let's jump right to line 35 here. I put a 3 here accidentally. No, not accidentally. I just messed up the formatting. I forgot a comma. Int box type. There's an error in line 45 now. Down here. Right, I need a semicolon there. And now accessing the box type down here is not valid because the box type up here, I think I cannot define it like this. I need to separate out different types. Yeah. And let's see which errors remain. Invalid initializer, get distance, distance result, distance undeclared. Did you mean get distance? If distance smaller equals 0, get distance. Yes, if distance, let's jump here. If result dot distance is smaller than or equal to 0. Okay, there's still an error. Why? Invalid initializer, player angle. Inline 116, unknown type color. Why is this? Do we need to use STL color maybe? And this seems to do it. Now it opens up a plethora of new errors. Incompatible types when assigning to... Ah, no, of course, the color is not an STL color, it's a uint32. I lost my mind already. Invalid initializer, get distance. So that's hopefully the last error. Invalid initializer, distance. Result, get distance. What is that? Invalid initializer. Let's jump to the line and see. Distance result, get distance. Let's see. Oh, yes, it needs to return a distance result here. And where does it return a distance result? Here. Yeah. Let's make it return a distance result. -1, box type 0, or box type -1 as well. Same thing here, and wherever it returns -1, this wall detected equals 0, equals 1 doesn't even do anything. We can just probably delete it and make it a while true loop, because it has to return at some point, at least when the render distance is achieved, is overcome, or surpassed is the better word here. Then we return the render distance at the ray distance here. Distance result, ray distance, and the box type is map cell y cell x. Okay, there's still an error. Let's see what that error is. Get distance incompatible types when returning type double. Of course, down here there's yet another one. So let's return an erroneous object here as well, or maybe even null, because this will never be called anyways. Why doesn't this work? Oh, it's incompatible. Okay, then let's return this distance result there. And let's see, still an error. Hope it's not. Hope it's the last one. Incompatible types when returning type double. There's another one. And now it's an unused variable when the wall is detected, which we can remove because we don't need it anymore. If we compile now, this compiles now without a warning. Let's see if it works, guys. Raycaster. We still draw all the walls white. Why? I mean, it's awesome that it works. I don't get why they are being drawn white. Did I undo the color accidentally? The color drawing. Draw a vertical line here. And then we draw the rectangle based on a color. Draw vertical line. Color is passed here. And comes from here. Here we set the color white, color blue, color red. What did anything happen to the map? No, we have a couple of different box types in there which determine the colors. So we need to let's check up here. Yeah, those are definitely different from white. I don't understand why the boxes are still all drawn white. Where's color white used? Maybe that is insightful. Only here. So the result of the box type is only, it's only ever 1. Why? Okay, we need to find out from the get distance function. So apparently, of course, we only check is the ray inside a wall in case the value is equal to 1. So of course only the walls where the value is 1, the cells where the value is 1 will be drawn. We need to check is it bigger than 0, because 0 is nothing. And anything beyond that is a wall of a different color. Boom, boom. Double heart pounding. Boom, boom. Guys, if this works, then I've been sitting on this project for so much time now. If this works, I'll freak out. And this is, why is it green? I don't want green. I want blue. Why is it green? R, G, B. I don't get this format. What if I do 0x, R, red, green, blue? Is this maybe blue? I'm half guessing this at this point. Color, blue, RG, blue, or this. Ah, this is blue. Okay. All right, guys. And one more thing before the final test, I want to increase the player's rotation speed. Let's make him rotate at 3 times that speed and move at double the speed. And let's reduce the frame rate a bit by reducing the SDL delay. Let's reduce it to 5, let's say, and let's see how this project has turned out. So let's have a look. We can rotate around the scene here, have a look around this. We can move into the scene. We can observe the different boxes that we have here. That's awesome. I don't get why this one is changing color. Oh, I know why. That's because that is data that is outside of the map that we haven't defined yet. So we need to move into our well-defined map here. Yeah, this looks good. No, okay. Let's for a final test. I hope this will now look halfway decent. Let's set the movement speed to something like 1, the rotation speed to something like 1, and then compile and start the raycaster. Let's move into the scene, and as you can see, we have a working raycaster. There are many details that we haven't implemented yet. For example, boundary checking of the map, things like that. But overall, we have nailed the foundation of raycasting, in my opinion. As you can see, we have a nice 3D view of the world that we have defined for us. It looks quite interesting. And of course, it's a simpleton map, but it's a 3-dimensional raycasted world. And it is all that I wanted to achieve in this video. And if you also want to code so nice C projects, then have a look at the no-nonsense C programming course linked in the description down below. It's an awesome course that takes you from zero C knowledge to a capable C programmer, such that you will be able to program these kinds of projects yourself. And most of all, it does not rely on theory. We will spend zero time in PowerPoint slides. We will be 100% of the time in the terminal, and you will learn all the practical coding stuff from me. All right. So for practical C programming, have a look at the no-nonsense C course in the description down below. I hope you enjoyed this video, and see you next time. Bye bye.